This section we start with the motor, part B. This is a typical mechanical characteristic of the induction motor. You can see this is a torque, zero torque, maximum torque. And here is the speed, zero speed, synchronous speed. And at this point, the slip is zero, and this zero speed, the slip is 1. And normally, the motor will be working on this area. For example, here is a T rated torque. So normally this area sometimes a little bit overload, and this is a stable area. We call it stable area. The motor can run in a stable condition. Now we're talking about the operation quadrant. This is the example. This is the elevator, and here is the cab where people stand inside the cab. Is a counterweight. And we have definition, the speed, this direction, we define as a plus. And also torque. If the motor torque is like this direction, we define as a plus, positive. So scenario 1, quadrant 1. If the cab goes this direction, and the weight of the cab is higher than the counterweight, that means the motor need to pull up the cab. So the torque goes this direction. The torque is positive, speed is also positive. So this is quadrant 1. The second scenario is the weight of the cab is less than the counterweight. That means the motor torque will be like this direction to make the system balance, to lift in the counter speed. Otherwise, if the motor did not generate torque with the direction, then the counterweight, because is heavy than the cab, will pull down, will go down and pull up the cab. So that means the torque is negative, the speed is positive, still go up. So that will be in the quadrant 2. Torque is negative, speed is still positive. So same, we have quadrant 3 and quadrant 4. Quadrant 3 and quadrant 4, speed is negative. That means the cab will go this direction. Okay, the torque you can either be positive or negative. And then here's we talk about the constant torque. As we know, the synchronous speed of the motor is proportional to the frequency of the motor frequency. And frequency number of poles slip. So this is a rated frequency and the rated synchronous speed. And if we reduce the frequency, the synchronous speed reduce, also the speed reduce. Then we have a lot of different curves. But normally, the maximum torque for each curve will keep almost the same. So this is why we call it constant torque. That means the ability of the motor the maximum torque motor can generate will be almost constant. So we call it constant torque. And if the frequency is higher than the rated frequency, then we have these curves. But because the frequency, you increase the frequency, but the voltage you cannot increase because of the limitation of the drive, also the limitation of the motor. Normally, the terminal voltage of the motor cannot exceed the rated, or a little bit higher than the rated. Otherwise, motor have the overheating because of the saturation issue and also the insulation limitation. So that means the flux, because the flux is proportional to voltage divided by frequency. So this one is almost constant. You increase this one, and the Fourier decrease. So when the Fourier decrease, that means the torque decrease. So that means, when you increase the frequency, but the maximum torque decrease. So this area we call the constant power. Constant power means because the torque is proportional to power speed. So this one constant, this one increase, torque decrease. So this is why we call it constant torque, constant power. And this is we call the equivalent circuit of the three-phase induction motor. Here is the motor voltage, frequency, rotation frequency, stator resistor, leakage inductance, state leakage inductance for loader, magnetizing inductance. And this is the identical rotor resistor. The rotor resistor divided by S is slip. And when there's no load means motor speed is same as the sync speed, and the slip is 0. Slip 0, this one is open circuit. That means there is no load current, only magnetizing current. If the rotor is rocked, that means there's not running on the road. For example, when the motor just starts, the speed is 0. The rotor is at standstill. So slip speed is 0. So slip is like this: sync speed, sync speed. So if this is 0, that means slip is 1. So slip 1, the maximum slip. So that means the lowest resistor on this part. That means the highest current on the roadside and the highest total current. So this is a two opposite situation. And this resistor we can convert into two resistors in series. Resistor and the resistor multiplied by this. And here we have another formula, PM. PM is the magnetic power, which representing the power converting from stator to rotor. And the PS we call the slip power, is PM multiplied by S. And PM is the mechanical power. Mechanical power is PM multiplied by 1 minus S. Okay. So PS plus P mechanical is equal to PM. So here we can see the power on this resistor representing the PM. This resistor represents PS. This is P mechanical power. See this one plus this one and equals this one. And the relation between this one and this one is PM multiplied by S equal to this one. And this one formula, this formula representing the relationship between this power and this power. And also, the torque, motor torque, is equal to the mechanical power divided by the rotating speed. It also equal to the total power of the electromagnetic power divided by the cyclic speed. Same, because omega r is equal to 1 omega. Actual speed, cyclic speed, slip. Then also the relationship between P mechanical and PM is also P mechanical is equal to 1 plus PM. So those two are the same. This formula is here. Okay, this is all for today's section. Thank you. Bye-bye.